In set theory, a branch of mathematics, an Urelement or Urelement is an object that is not a set, but that may be an element of a set. Urelements are sometimes called atoms or individuals theory. There are several different but essentially equivalent ways to treat Urelements in a first-order theory. One way is to work in a first-order theory with two sorts, sets and Urelements, with a B only defined when B is a set. In this case, if U is an Urelement, it makes no sense to say although is perfectly legitimate. This should not be confused with the empty set where saying is well-formed because is a set, whereas U is not. Another way is to work in a one-sorted theory with a unary relation used to distinguish sets and Urelements. As non-empty sets contain members while Urelements do not, the unary relation is only needed to distinguish the empty set from Urelements. Note that in this case, the axiom of extensionality must be formulated to apply only to objects that are not Urelements. This situation is analogous to the treatments of theories of sets and classes. Indeed, Urelements are in some sense dual to proper classes. Urelements cannot have members whereas proper classes cannot be members. Put differently, Urelements are minimal objects while proper classes are maximal objects by the membership relation Urelements in set theory. The Zermelo set theory of 1908 included Urelements. It was soon realized that in the context of this and closely related axiomatic set theories, the Urelements were not needed because they can easily be modeled in a set theory without Urelements. Thus standard expositions of the canonical axiomatic set theories ZF and ZFC do not mention Urelements. Axiomatizations of set theory that do invoke Urelements include Kripke-Platek set theory with Urelements, and the variant of von Neumann-Bernays-Gödel's set theory described by Mendelssohn. In type theory, an object of type 0 can be called an Urelement, hence the name atom. Adding Urelements to the system new foundations to produce NFU has surprising consequences. In particular, Jensen proved the consistency of NFU relative to Peano arithmetic. Meanwhile, the consistency of NF relative to anything remains an open problem. Moreover, NFU remains relatively consistent when augmented with an axiom of infinity and the axiom of choice. Meanwhile, the negation of the axiom of choice is, curiously, an NF theorem. Holmes takes these facts as evidence that NFU is a more successful foundation for mathematics than NF. Holmes further argues that set theory is more natural with than without Urelements, since we may take as Urelements the objects of any theory or of the physical universe. Quine atoms. An alternative approach to Urelements is to consider them, instead of as a type of object other than sets, as a particular type of set. Quine atoms are sets that only contain themselves, that is, sets that satisfy the formula x equals x. Quine atoms cannot exist in systems of set theory that include the axiom of regularity, but they can exist in non-well-founded set theory. ZF set theory with the axiom of regularity removed is compatible with the existence of quine atoms, although it does not prove that any non-well-founded sets exist. Axel's anti-foundation axiom implies there is a unique quine atom. Other non-well-founded theories may admit many distinct quine atoms. At the opposite end of the spectrum lies Boffer's axiom of superuniversality, which implies that the distinct quine atoms form a proper class. Quine atoms also appear in Quine's new foundations, which allows more than one such set to exist. Quine atoms are the only sets called reflexive sets by Axel, although other authors, e.g., John Barwise and Lawrence Moss, use the latter term to denote the larger class of sets with the property XX.